Hello and welcome everyone to reInvent, and thanks for joining us on this session on transactional data lakes. My name is Radhika Ravirala. I'm a product manager with EMR Glue Athena services, and I focus primarily on the security of these engines. I'm joined on stage by Gio.
Hi, I'm Gio, Matteo Fumarola. I'm a senior manager in AWS.
Thank you, Gio. So before we begin the session, a quick show of hands. How many of you are running data lakes today? Wow, that's an amazing 99%. And how many of you are using Apache Iceberg with your data lakes? Okay, so I see quite a few hands, and I hope you'll have something to take away after this session. So in terms of the agenda today, we are going to walk down the memory lane, take a brief history of what transactional data lakes are all about. Gio will do a deep dive into open table formats. We'll also cover, from a product perspective, how to build and optimize your data lakes and how to enrich them with open table formats. And we'll wrap up the session with some key takeaways and Q&A. So if you go back in history, you will see that the first origins or the early stages of a transactional data lake was in the form of a relational database system. So customers used relational database systems because they were foundational blocks for transactions. They were designed to help you run transactions, and they provided primitives like insert, update, deletes that made them a good choice for high volume transactional environments. But they were not without any drawbacks. They had a limitation, which is the inability to run large, complex analytic queries over aggregated data. Now, to address this problem, we have seen the rise of OLAP systems, or on-premise data warehouses. Now, data warehouses addressed these issues, and they excelled at managing structured data as well as providing that vital capability to run your complex queries and analysis, which powered your BI systems. However, the underpinning for a data warehouse is RDBMS, and RDBMS are hard to scale. You typically have one primary node that supports all the write requests, and then you have a primary and a bunch of replicas that support all your read requests. Now, scaling is expensive here simply because in terms of cost as well as time. So Hadoop emerged as a solution to this limitation, where it allowed you to scale elastically and also provided a distributed file system, which enabled you to kind of scale your compute and storage independently of each other. So with the Hadoop, we also saw a lot of customers developing data lake architectures, which helped you not only manage all these kind of applications that were already supported by data warehouses, but Hadoop and the data lake architectures allowed for an important concept, which is decoupling of storage and compute, and also supporting a lot of variety of data, which includes semi-structured, unstructured data, in addition to the structured data that you're already used to. However, Hadoop and the data lakes also have an inherent limitation, which is, if you think about it, data lakes do not provide the consistency and the integrity that a data warehouse provides, because they lack the ACID properties. The atomicity, the consistency, the isolation, and durability are absent in data lakes. Similarly, if you look at the data layout in a data lake, it doesn't offer itself for high performance. That's another drawback. The third one is being able to govern your data. Like in a data warehouse, because it is an RDBMS system, you can define permissions, and no such thing was available. You can only do it at a file level. on data lakes. So the advent of the emergence of the cloud and the versatile nature of the object storage did lend customers a hand in building more modern architectures like Lakehouse. And the Lakehouse allowed customers to combine the versatility, the low cost of a data lake with the benefits that you already get from data warehouses. Now, this combination or this convergence is very powerful, but Lakehouse is not just about integrating a data lake and a data warehouse. It is about connecting your data lake with your data warehouse and all the other capabilities that you currently use, be it in terms of non-relational databases, big data processing, log analytics, machine learning, as a coherent, wholesome solution. And so to fully support a lakehouse architecture, something needs to be fixed in the traditional data lakes. And those are the three challenges that we currently see in data lakes, which is ability to do continuous updates. Your data is arriving from a variety of sources, and it is arriving fast. You need to be able to update your data lake and keep it fresh. You need consistent performance, so the lot of small files that are coming in every second can be compacted very quickly, which will give you a better performance, and partition updates, which is a commonplace in a lot of data architectures. And then you also need to comply with regulations, which means that you need the ability to delete data when desired. So in addition to these challenges, we also have customers asking for other requirements because their architectures are also evolving and they have new needs, which is they're asking the fundamental question, which is, can we have a single platform that can run transactions and analytic workloads on a data warehouse, and can data warehouse support open source flexibility? Similarly, can data lakes support end-to-end governance and also add performance and ACID-like properties, which are the core fundamental features of a data warehouse? So you need the best of two worlds in order to make your lakehouse architecture really work for you. And so that's where transactional data lakes come into picture. Transactional data lakes are powered by open table formats, which provide the transactional support and simplify your data lake optimization and management. In the field, there are three popular or prevalent open table formats, which include Apache Hudi, Apache Iceberg, and Delta Lake. And these three open table formats provide you with database-like capabilities on your data lake. Gio will dive deep into how these OTFs provide those capabilities. But in the meantime, let's take a look at in which use cases you need such capabilities, starting with modern data use cases that is streaming ingestion. So streaming ingestion is a very popular use case with a lot of organizations. This is where you have a ton of streaming sources, streaming data continuously through your streaming services such as Apache Kafka. You have Amazon MSK, Amazon Kinesis Data Streams, and Kinesis Data Firehose. And these streaming services, as they are continuously streaming this data, they are ingested and processed by stream processing engines like EMR, Glue ETL, and Amazon Managed Service for Apache Flink. And then they are stored, curated, cataloged, and secured, and then they become ready for consumption through your consumption layer that includes a variety of services such as Redshift, Athena, EMR, and SageMaker. But to support these streaming ingestion use cases, you need to be able to make atomic changes, because as the streaming data, teeny tiny streaming updates are becoming available, you need to be able to apply these changes immediately. You need to be able to provide a snapshot for the readers to read the data and query the data whereas the writers can do their writing at the same time. So you need isolation between them. Again, a characteristic of a database. You need high throughput ingestion because this data is arriving very fast. You need to be able to compact small files for performance, and you need to be able to do row-level inserts and updates. We'll see more about this in the coming slides. The second use case where transactions are very common is to be compliant with data privacy regulations. So you have your monthly GDPR deletion pipelines or CCPA deletion pipelines, which are run on a regular basis as batch deletion jobs through the stream processing services like EMR, Glue, and Flink. And you need to be able to delete those, make your data lake up to date, make sure the metadata is updated as well, and be able to make it available for consumption. Now, complying with data privacy regulation is notoriously hard because it's like finding a needle in a haystack, because you need to first find the records for a particular user, which means that entails doing a full table scan on your data, which is expensive. And once these files are located, you need to be able to delete those records from the table. And with big data frameworks like Spark, it requires overwriting an entire partition. And so compliance, to meet the compliance needs, you need to be able to have concurrent writer support as well as row-level upserts and deletions. In addition to this, we are also seeing a new breed of applications being added to your data lakes, which includes the GenAI applications using Bedrock, the foundational models that are constantly querying your data lake, and your data needs to be fresh and available to support these new breed of applications. So organizations are seeing transactional data lakes take the center stage to support a variety of applications that includes your log, analytics, data warehouse, relational databases, and generative AI applications. So let's take a look at how some of these transactional data lakes are implemented in real world by some of our customers. So here is an example from Zoom, who implemented streaming log ingestion and efficient GDPR deletes using Hoodie on Amazon EMR. The challenge they had was they were ingesting huge amounts of application log data, and also had a requirement to meet from their security teams to delete records to comply with the GDPR. And so the solution they implemented was using EMR, Athena, and Apache Hoodie to build an optimized and scalable infrastructure to efficiently delete the data. And by implementing this solution, they were able to cut down their storage needs by 90%. And they were able to accomplish this very fast at a record of 1,000 records deleted within less than 2 minutes. Another example we have is from Orca Security, who were building a petabyte scale data lake, including managed data retention and optimizing streaming injection. So they had a ton of data silos that they wanted to consolidate, and to support the consolidation of this data lake and to implement their use cases on data retention, they used EMR, Athena, S3 with Iceberg. So they did a comparative analysis, and Apache Iceberg suited their use cases much better. And so they chose Apache Iceberg to build a scalable, cost-effective, and performant transactional data lake. And so as a result of implementing this, they were able to reduce their pipeline management and query costs by 50%, which scaled seamlessly, and they were also able to onboard newer use cases onto this petabyte scale data lake. So with that, I'll invite Gio to talk a little bit deeper on open table formats and how they solve some of your data lake challenges.
Perfect. Thanks, Radhika, for the first part of the presentation. And let's change gears and let's do a dive deep on the slight technical aspect of open table format. And I want to give a primer of this. Now, as Radhika mentioned, there are several requirements for our open table format to be efficient. First of all, they have to support record level update and deletes. They have to provide the ability to have data integrity and consistency, provide the ability for the engine to do fine-grained access control, as well evolving the table over time and managing file and provide amazing performance. Now, this is my favorite slide, and it represents the architectural component of a distributed query engine. Now, on top, we have your favorite query engine where you guys run your job or your query. And usually there are Spark, Apache Flink, Trino, Athena, Redshift, HBase, and so many others. This query engine runs query or job on top of a table registered on a catalog. Some examples of catalog are Glue Data Catalog or Hive Mena Store. These tables are a set of objects, and these objects are stored in file format like Parquet, Avro, ORC, JSON, CSV, and so many others. And of course, these objects are located in storage layer like HDFS or Amazon S3. Now, where does open table format fit in this? Do we want to take a guess? It fits between the catalog and the file format. Now, I highlighted the Hoodie, Iceberg, and Delta in purple while I kept Hive in white. Now, usually tables are in a Hive format. That means all the objects within a folder they belong to the same table or the same partition. While Hoodie, Iceberg, and Delta, they provide a concept called manifest. Now, between Hoodie and Delta and Iceberg, they have different nomenclature like checkpoint, check file, and so on. However, a table at a specific point of time points to a manifest. And the manifest literally summarizes what's the status of the table. In this case, the table has only 4 objects. Let's say somebody comes and does an insert. Now, the insert adds 2 objects to the storage layer, and the open table format updates the manifest point to the new manifest. Another operation along the way it happened as update or delete, and the manifest now keeps track of 7 objects. Finally, open table format provides a function called compaction, where it compacts the existing object with the new one and create new ones as needed. In this case, it deleted from the manifest an original object, an original white object, and the newer one, and create 2 turquoise objects. Now, however, the older objects are still kept in the storage. However, in the manifest, we will see only and only the 5 objects within the dotted lines. Why open table format keeps these objects still in storage? And one of the reasons is time travel. Now, at this moment, the table is the last version with 5 objects. However, open table format provides the ability to do time travel query. That means running a query in the past. And in this case, the query was run against a time of the second version of the manifest. Now, there are customers that they like time travel query, but they may want to save some storage space and storage costs as well. And open table format provides the ability to do vacuuming. That means clean up the entire storage of a needed object and a needed manifest. Now, this is kind of one of the main takeaway of this session. AWS, actually, let me step back. We have heard and read online blogs or opinion, Iceberg, Hoodie, Delta, and so on. What's the best one to go for? And one of the main takeaway I would like you folks to take on from this session is that AWS supports all three open table formats. Athena supports all three. EMR supports all three. GlueETL supports all three. However, AWS is prioritizing the features launch on Iceberg first. For example, EMR serverless launch fine-grained access control with Spark, and the launch was done at the same time with Iceberg. Now, why AWS is prioritizing the launch of Iceberg first? And the reason is customer interest, customer feedback, performance enhancement of Iceberg itself, as well as the open source community. And I really like this graph on the right side or left side of the audience, where AWS is a big contributor of Iceberg and as well is part of the community. Now, let's talk about Apache Iceberg. And I want to give some of the main features that Iceberg provides by default, or they are out there in open source. And I want to go back to the first slide, my first slide, the requirement. We said that the open table format, Iceberg in this case, has to provide efficient record level update and delete. Of course, there are several use cases, for example, ACID transactions. Now, Iceberg is a multi-engine open table format and provides the ability to run delete from, merge into, and update. Now, I promise this is the only really technical slide in the deck. And if you remember some previous slides where open table format was a block, that block is summarized within these two dotted lines. Now, there are three layers in Iceberg, where Iceberg has the first part is a metadata file where we store the snapshot that are the point to a state of the table over time. Each snapshot has a manifest list which contains a list of manifests, and each manifest points to a file or to a list of files that got added in that moment. We will see in a moment how these manifests get tracked within Iceberg. Now, Iceberg provides two main concepts, and you guys have heard about both: copy on write, and merge on read. In a copy on write scenario, what happens is that the open table format tells the engine to rewrite the entire data. For example, there is an update or a delete or insert. Iceberg is telling the query engine to literally rewrite all the needed data files. Now, this has, of course, some trade-off. For example, during write operation, we are rewriting the data, and writes are way more expensive. While on the reader side, there is no impact, because the query engine does not have to go through all these new objects to understand what happened to the table. On the other side, there is a merge on read. In a merge on read scenario, during our update, delete, or merge, a new object gets added, and this object is a log file, and usually it tracks what happened to the table. For example, update every ID equal to 5 to this value, or update the address to a specific street, and so on. In this case, writes are really, really fast, and this is usually common for streaming case scenario, while on the write scenario, on the write case, the query engine has to scan all these log files to understand what happened to the table. Now, let's see what happened to the manifest during these two operations. And I will go first with a copy on write. I promise this is the last technical slide, really technical slide that I will present. First, as I mentioned, the new file gets rewritten. Second, a new manifest gets created. And all of these within the two dotted lines get handled by Iceberg behind the scene. So a new manifest file gets created, and the manifest file points to the new data file that is literally the new data file with all the rewritten records. A new manifest list gets created that points to the manifest file. Finally, the metadata file gets created, and now has 3 snapshots. Of course, S2 got created and points to the new manifest list. This is what happened during the copy on write. On merge on read, directly the new delta file get created, or log files. They have different nomenclature. They get created and added to the storage layer itself. Iceberg now creates a manifest file that points to both of them, and a manifest list that now points to the older manifest list and to the new one. And finally, a metadata file that points to the new manifest list. Now, all of these happen behind the scene. However, one of the main takeaways is that Iceberg supports both merge on read and copy on write. Now, let's change gears and let's talk about another requirement, evolving the table schema over time. And now there are several use case scenarios like data normalization, streaming case scenario, or compliance as well. Iceberg provides 2 amazing features: schema evolution and partition evolution. And let's tackle first schema evolution. Iceberg provides the ability to change the schema of a table without have any side effect. Does not require to do any data manipulation or data movement. Independently, you can add, drop, rename, reorder of data column. And this is just a metadata operation. And Iceberg, by keeping track of the status of the table over time, after a specific point that the admin updated the column, updated the schema with the adding or drop a column, Iceberg remembers these changes and will allow the query engine to pick the right column if the column is there or not. The other feature that Iceberg provides is partition evolution. Now, let's pick this case scenario where we have a table that contains all the sales done by our organization over time. And this table is partitioned by month. In this slide, we have January 2023 and February 2023. However, after a little bit, we realized, this organization realized that having a table structure and partition by month is no longer scalable. Why? Because so many sales happen, or the jobs and the query that run against this table, they don't meet a form of SLA. What happened at this point is that the administrator decided to alter the table by changing the partition from month to date. And on March 1st, a new partition gets created. And by the end of the month, there will be 31 new partitions. And all of this is being done without additional costs as moving the data, migrating table, recreating all the queries, and so on. And Iceberg provides the right knowledge to the query engine to run queries like in this format. For example, we want to run a sec star from the sales table where we get all the sales between February 11th and March 18th. We split the query in half, and we get the right knowledge and the right object to the query engine to run that query. Now, again, partition evolution is free of side effect, and it's just a metadata operation. The next requirement is data integrity and consistency, and there are several use cases. For example, data tracking and rollback change. Now, this is a feature that actually AWS contributed to open source. Now, as I mentioned before, each transaction, insert, update, delete, merge, and compaction, creates a new snapshot. And let's pick this timeline of events. At the end of the month of January, we have S1, that is the snapshot of the end of the month. We have other two snapshots that happen within February. S4 happen at the end of February, and we have S5. The administrator decides to tag a specific snapshot with end of the month label. Now, another snapshot comes in March. Finally, another snapshot comes at the end of the month in March. And the administrator decides to tag S7 as end of the month 2024. At this point, the administrator does another operation that is expire snapshot that deletes any snapshot that do not have a tag that are no longer needed. In this way, we can still do time travel. However, we are doing time travel to a snapshot that points to a tag that the administrator decides. Now, branching and tagging is similar to how Git works. And we will see how Iceberg handles branching. Let's pick the same case as before, where we have 3 tags. Let's forget about the needed snapshot. An administrator picks the snapshot as S7 and decides to branch it out to create a new, kind of a new table with a different branch. Now we have a different version of the table where it's called T1. After that, we do another operation on T2. Finally, we do a compaction. Now, a possible use case for this is auditing. For example, we take the original table, we spin it off to a different branch, we delete all the columns that the auditor cannot and should not have access, we compact the data, and now an audit purpose can happen. Finally, the last requirement is performance, which is actually one of my favorite topics. Of course, as a use case scenario, who doesn't like amazing performance? Iceberg provides two features to improve performance. One of them is hidden partition. Let's pick this case scenario. And we have a table that has several columns. For example, levels, event time, and event date is a partition of this table. If we try to run this query, where we filter by event time, what happens is that Hive tells the query engine, you have to scan all the data. To overcome this, we add a new filter, event date equal to 2018, the 1st of December 2018. In that case, the query engine will only do a partial scan. Now, there is a correlation between event date and event time. And in Hive, they are required to have 2 different columns. While in Iceberg, and this is the concept of hidden partition. Event date is no longer there. We have event time. And the partition is done by a function, day of event time. And by running the previous query, in automatic, we get the benefit of a partial scan. Lastly, this is actually my favorite feature in Iceberg, and we have contributed kind of 3 versions of it. Let me dive deep pretty fast. As you guys are aware, Hive stored the table in this format that is kind of a tree. Table, partition by year, partition by month, date, object, and so on. However, all the objects have the same prefix, table, data year. And what happens is that for S3, because they share the same prefix, all the requests will land on the same node. And what happens is that error 503, throttling, reduced performance. Iceberg adds the concept of randomized prefix, where this is just an example. However, Iceberg adds the concept of randomized prefix, where Iceberg adds a prefix before every partition. Now, in this way, the query engine spreads the requests on S3, and of course, there are better performance. Now, just to add, recently, we have added in Iceberg open source, and with the MR 7.4, we have added the 3rd version of this feature. And one of our internal customers, Amazon Ads, released a blog where they demonstrate a drastically reduce of error 503, as well as 22% performance improvement. Now, we have seen how Iceberg has all these features in open source. However, Radhika is going to talk on how we are optimizing transactional data lake with OTF in AWS.
Thank you, Gio. So Gio and I both represent the product here. And in this section, we want to really walk you through a product lens on how we are trying to build features that will help you optimize and enrich your data lakes with open table formats, starting with performance. So in all my years at AWS, I've never heard from a customer that they are happy with the performance they have and that nothing else needs to be done anymore. Performance is an ongoing improvement that we take it as a goal, a yearly goal. And this year as well, we have taken a goal to improve the performance of Spark, with the addition that we also include open table formats in our benchmark testing. So in the beginning of the year when we launched 7.1, 7.1 was about 2.7 times faster than Apache Spark, OSS Apache Spark 3.5, 5.1. With Iceberg 1.5.2 based data sets. Now, when we compare that with the latest release on EMR, which is 7.5, we have increased our performance up to 3.6 times than the latest Apache Spark version, which is 3.5.3, working on Iceberg with 1.6 data sets. So this is an ongoing improvement that we will have from a product side to make sure that the Spark applications with your open table formats are performant and give you that edge in terms of running your applications faster, thus enabling you with cost optimizations as well. So in order to get to these performance numbers, there are a number of features that Gio's team has been working on, and they include shuffle reduction, redundant scan elimination, optimized data structures, optimized code generation, adaptive joint selection, and Bloom filters, adaptive Bloom filters, and so on. There are a variety of features that we are continuously working on to improve the performance every year. And these performance improvements are enabled by default, which means that you don't have to do any other configuration to get these benefits. And with each EMR runtime release that we have, we are 100% compatible with OSS Spark APIs, which means that you should be able to use any of our runtimes and get these benefits. And that includes all EMR deployments as well as the Glue ETL engine that runs Spark. If you recall, in the previous part of this presentation, we talked about how governance is a major concern on data lakes, and with the OTFs, that is even more challenging because you want to be able to define permissions at a granular level. And when the data lakes came about, we had permissions that you could only define at a file level. And so data access is also important to a lot of enterprises because of the explosion of data, explosion of personas, as well as the acceleration they're seeing in the number of applications that they want to bring about. So as a result of this, we have two different types of fine-grained permissions available with your analytic engines. One is the coarse-grained permissions with open table formats, and that is available through a feature called S3 access grants. This feature was launched last year, and it allows you to enforce granular S3 access controls at scale, which means that you will be able to define permissions on S3 prefixes and enforce them through our engines like EMR. On EMR, we support Hudi and Delta Lake through our connector for S3 called the EMRFS, and for Iceberg, we support it through S3 file IO, which is a connector to S3 when you're using Iceberg-related clients. And so you can grant permissions directly to your identities from external corporate identity directory as well, such as if you are using IDC, Identity Center, IAM's Identity Center, with the trusted identity propagation, you can bring all those identities and give them permissions at this coarse-grained level, and that also gives you the ability to do end-to-end auditability. We also have fine-grained permissions. Fine-grained permissions refer to permissions that you can define at table, row, column, and cell level. So if you see this architecture, you have your ingest mechanisms available through our stream processing services and batch processing services. You can put the raw data in S3, and you can impose fine-grained access controls using lake formation and have these stream processing engines and the batch processing engines enforce those policies for your Hive tables and Apache Iceberg tables when you're working with your Spark jobs. So this is a new feature that we launched with EMR Serverless in summer of this year, and we are launching it with Glue 5.0, which just launched yesterday. And so we are very excited about this feature and how customers can go and define granular permissions on their data lake assets with open table formats. Another feature that we are excited about is the ability to define multi-dialect views. This is provided through the Glue Data Catalog, and it's a feature from the Glue Data Catalog called Glue Data Catalog Views. It allows you to define the view once and use it with multiple analytic engines like Redshift, Athena, and very soon with EMR and Glue as well. And so the idea behind the views is for you to define these views once and be able to query these views from multiple engines of your choice. And you can protect the data through the base tables as well as through views using fine-grained access controls defined in lake formation. And these views can be shared across accounts and also linked across regions. But there's more. So the Glue data catalog itself has been working very hard at bringing about multiple features this year, and they include multi-catalog support for supporting your change data capture. So if you think about the Glue data catalog today, there's a one-to-one mapping between the catalog and your AWS account. So the hierarchy is very flat, and per account, you only have one catalog that you could define. So starting this month, we have added support for multi-catalog support, which means that you can have multiple catalogs within an account, and those catalogs can include federated catalogs that you are federating from external sources as well. We have Glue Data Catalog has also implemented automated compaction for Iceberg tables. They have enabled snapshot retention, which will help you reduce your storage costs. We have a metadata and data federation, which will allow you to federate to external sources with Athena to get and implement FGAC functionality on that. And also, we are constantly updating the statistics on the tables in the Glue Data Catalog to give you much better performance. With that, we'll enter into a new topic, which is about interoperability with AWS Analytics. What this means is, it is good to have open table format support with our data lakes, but you may be wondering what other AWS services support these open table formats and how do they interoperate. And so we are very excited to talk about SageMaker Lakehouse, which was launched yesterday in the keynote. And the idea behind SageMaker Lakehouse is to help you unify all your data across multiple sources for your analytics and AI initiatives with a single copy of data, regardless of how and where it is stored. You can use your preferred choice of the analytic engines, define fine-grained access control permissions, and be able to do zero ETL for ingestion, federation, and sharing. So you are empowered to bring your preferred Apache Iceberg compatible tool to query SageMaker Lakehouse, and be it Jupyter Notebooks, be it analytic engines that are supported on AWS, or Bedrock APIs to tap into all of your data. And as an added benefit, you also get integrated fine-grained access control on your data that is reflected across your tools. So if you look at, if you peel the onion and see Amazon SageMaker Lakehouse is a combination of, it combines the benefits that you get from Redshift managed storage with the storage that is already available in Amazon S3 to give you that unified data access for your RMS tables, the Redshift tables, as well as the S3 data, and through multitude of our tools. So we also support open source tools here, which means that open file formats like Parquet and ORC, as well as Iceberg. And you can also bring your third-party access with Apache Iceberg APIs, which means that any Apache API compatible tool can tap into SageMaker Lakehouse to query the data. And it's integrated and secure with fine-grained access control permissions using both the Glue Data Catalog and Lake Formation. So no changes necessary to your existing data architectures. You can simply start using this either directly from SageMaker Unified Studio, which is in preview, and be able to leverage the Lakehouse architecture as you see it today. And so this is a view of the components that underpin the SageMaker Lakehouse. It includes a flexible storage for diverse workloads. We have a unified technical catalog that manages all your data. We have integrated permission management system to securely share your data. And we have support for Iceberg APIs to access this data from our analytics services and third-party applications as well. So another support that we have added in terms of enhancing your data lakes is the ability to write to Iceberg tables from Firehose. So if you're using streaming services, Iceberg support is added through Firehose. It gives you the ability to create new tables and columns in your destination S3 bucket directly. It supports schema evolution, filters out the PII data, gives you the ability to connect to databases within your own VPC, and also supports databases like MySQL and PostgreSQL. So we have a whole slew of services that already support this, which are already in GA, and there are other databases that are currently in preview, which we will also GA. And all these give you the ability to write to your transactional data lake in Iceberg format. But you might be wondering, what about Xtable and Delta Uniform? For those of you who have heard this term or not heard this term, these are new projects that are started in the open source community, and the purpose of these tools is to provide interoperability among the open table formats as well. So Xtable gives you the ability to read the metadata from Iceberg and Delta Lake. It's a project that was started by the company that commercialized Apache Hudi, and they have open sourced this project, and they are working on providing that interoperability so that you can interoperate between these three, or among these three open table formats as well. Delta Uniform is also another project that was started from the Delta Lake community, and the idea behind this is to provide you with that ability to read the metadata from Hudi and Iceberg for your Delta Lake tables. So these are new upcoming projects, and some of our customers are already exploring architectures using this interoperability, and we are excited to explore this area further and share more updates with you and on these two topics in the coming future. To recap, open table formats give you that ability to perform transactional updates, which are essential to implementing database-like features to your data lakes to bring the data freshness and to provide you with row-level updates. They provide schema and partition evolution. As Gio mentioned, schema and partition evolve continuously in data lake architectures, so open table formats support that. We are continuously optimizing these formats and through compaction and other performance improvements to bring about the speed that you need, and also do point-in-time queries with time travel feature that these open table formats offer. So why choose AWS for your transactional data lake? As Gio and I talked about, there is a comprehensive set of services that support this open table formats with the AWS ecosystem of analytic services. These are flexible. You can choose AWS managed or open source capabilities, as we have noted with the SageMaker Lakehouse example. We have a broad support with vast partner ecosystem. These are cost effective because we are continuously working on optimizations and improving the speed. You can get faster insights or real-time views of your business when you incorporate streaming architectures into your transactional data lake. We are constantly working on security to give you better controls on how you can add fine-grained access controls to your data, your metadata, and bring the data unification through SageMaker Lakehouse and SageMaker Unified Studio, so you could do it all from one place. And then there is no vendor lock-in with all these features that we are bringing in. So In all, AWS provides a great place for you to implement your transactional data lakes, and we can't wait to hear from you about what your transactional data lake experience and journey has been. And we look forward to working with you on this topic in the coming years. So thank you for joining us on this session, and Gio and I are happy to take questions. We will be here outside of the podium as well as outside of the room if you have additional questions, and have a great conference. Thank you.